Okay. Good afternoon, dear students. Today I will discuss some important topics from the numerical point of view. These topics are very important, not even for only university exam, but also from competition point of view. Right? So, first I will discuss isentropic efficiency of compressor and turbines. What happens there? Actually, in last lecture, we considered that isentropic compression and isentropic expansion. 1 to 2 isentropic compression and 3 to 4 isentropic expansion. But actually there is irreversibility in compression process and expansion process also. Why? Because there is fluid friction and other type of friction is present. That is why there will be irreversibility, and due to irreversibility the more compression work is required as compared to isentropic process. You can say here 1 to 2, right? Now actual process 1 to 2 days. It is mentioned here 1 to 2 days actual compression process, right? More work is required due to losses, due to irreversibility, system irreversibility, right? So actual process 1 to 2 days. Here temperature is higher and also entropy, right? Now what is compressor efficiency? Basically isentropic efficiency. That is what? Isentropic work required upon actual work required. This is ratio of isentropic work required to the actual work required. So isentropic work required upon actual work required. H2 minus H1 upon H2 dash minus H1. Enthalpy at this point, enthalpy at this point. So this is small H compared to this, right? Because you know the pressure line diverges. So H2 minus H1 upon what is actual H2 dash upon minus H1, right? And we can write it in terms of temperature also, because H is equal to CPT, right? And this was also assumption that isentropic compression is there. Next, so compressor efficiency T2 minus T1 upon T2 dash minus T1, right? Next, turbine efficiency. What happens here also? In isentropic process, we assume that there is not any irreversibility, and what will be work done from expansion from this point to this point. But actually, due to irreversibility, we will not get this much work. Actually, we will get work less than this, and it is represented by 3 to 4 days process, right? So this work will be actually obtained, not this. That is why what is efficiency? That is actual work obtained upon isentropic work obtained. So this is equal to actual work done upon isentropic work done. Enthalpy at 0.3 minus enthalpy at 0.4 dash upon enthalpy at 0.3 minus enthalpy at 4, and again you can write it in terms of temperature, right? So these are efficiency. 1 to 2 dash actual compression, 3 to 4 dash actual expansion, 2 dash to 3 actual heat addition. Very important. It will discuss it later. Next, combustion chamber. This is also very important, right? Now, in actual and ideal combustion, it is assumed that whatever heat is released by the combustion of fuel, that is equal to rise in enthalpy of the gases, right? So suppose that this is combustion chamber, MA mass of air enters after compression, right? Mass flow rate, CPA specific heat at constant pressure of air, T2 dash, any 0.2 dash here, because combustion occurs from here to here, heat addition process. So T2 dash and temperature is T2 dash. Combustion chamber, mass of fuel added, M suffix F in the combustion chamber, because for combustion, as you know, fuel addition is compulsory. In case of open gas turbine, combustion will be there, right? After 3.3, temperature at T3. Now here the air is entered, but here after combustion what will happen? Mass of air plus mass of fuel, total mass of gases Ma dot plus Ma, mass flow rate of air plus mass flow rate of fuel. And also this was assumption that Cp is constant throughout process but not in actual. So let Cpg is the heat at constant pressure for the combustion products. So what will happen now? Suppose that what will be heat released by the fuel, that is, as you know, mass of fuel multiplied by calorific value of the fuel. So mass of fuel into calorific value of fuel, right? And now combustion process is not 100%, means there will be some losses also. So let this is efficiency of combustion, right, after loss. So this is heat released, MF into CV into efficiency of the combustion chamber, right? So this is heat released by the fuel. Now for ideal combustion, this heat release should be equal to rise in enthalpy of the gases, right? So now total mass of gases Ma plus Mf into specific heat at constant pressure of gases into what is temperature here? T3, right? This is enthalpy of gases. And what was enthalpy at point 2 dash? That was mass of air into specific heat of air into temperature T2 dash, right? So what is the rise in enthalpy? This much minus this, right? Now sometimes numericals are given in terms of air fuel ratio. So we can divide both sides with the MF, mass flow rate of fuel. So this is CV into combustion plus here what will be Ma upon Mf. Mf से Mf cancel 1 plus Ma upon Mf into CpGT3 minus again Ma upon Mf Cpa into T2 dash, right? And what is this? Mass of air upon mass of fuel. This is air fuel ratio. So it is mentioned here 1 plus air fuel ratio Cpg T3 minus air fuel ratio Cpa. Actually this is important if in numericals sometimes air fuel ratio is given directly. So we can find out here. Now this equation or this equation is used for exact analysis, means considering the change in specific heat of the fuel and gas, right, air and gas. So this will be used for exact analysis. Sometimes approximate analysis is also done. In that case what? We assume that specific heat of air is equal to, specific heat of gas is equal to specific heat of air. So in that case what will happen? Cpg will be equal to Cpa, right? So we can take common from here that Mf for approximate analysis, Mf into Cv into efficiency of combustion chamber is equal to Ma plus Mf into यहाँ से Cpa आपने कॉमन ले लिया, we will get what? Into T3 minus T2 dash. Ma plus Mf Cpa T3 minus T2 dash, or in terms of air fuel ratio 1 plus air fuel ratio Cpa into T3 minus T2 dash. This is for approximate analysis and this is for actual or exact analysis, right? Okay. Now next, this was combustion chamber. Now suppose that the assumption was that there is no pressure loss in the combustion chamber. Sometimes in numericals it is given that some pressure loss is there. Suppose that initial condition was this, right, when the pressure is constant. Now suppose that this much is pressure less, means that is equal to P3. Suppose that this is P3 equal to P2, P3 dash. This is pressure loss in combustion chamber. Now what will happen there? For finding the pressure ratio on turbine part, we have to consider this pressure. That means P3 dash pressure at this point, and after loss, upon P4 is equal to RP. P4 and P4 dash is same, so there is no problem, right? And what will be equation? T3 upon T4 is equal to P3 dash upon P4 power gamma minus 1 upon gamma. Means for such type of numericals, when there is pressure loss in combustion chamber, we have to apply this relation for turbine expansion. Next, net turbine work, net work क्या होगा? Now there is gas, so net work, turbine work minus compressor work. Now this is important here. Means in case of turbine, we have to consider the heat of constant pressure of gas, and in case of compressor, we have to consider the heat at constant pressure of air. This should be minded, right? So these two are also important from numerical point of view, right? In next in this unit I will also prepare a video on the types of turbines, open and closed, their advantage and disadvantage. Some assumptions are discussed here, like that there is not any pressure loss, Cp, Cv, gamma are constant. These are discussed, and already in unit first these are discussed in this power cycles also. That is why I think that you are all aware. Thank you. All the best.